This is the lecture material for Chapter 7, Chemical Bonding and Molecular Geometry. In this chapter, I'm going to start off with a brief introduction. Then we'll talk just briefly about ionic bonding and covalent bonding. We'll draw some Lewis structures. We'll look at some formal charge and resonance, and sort of end up by talking about the strengths of the ionic and covalent bonds and how that relates to the molecular structure and polarity of a molecule. So bonds are the attraction of atoms toward each other to create a molecule. There are 4 different types of bonds. The first one we'll discuss is ionic bonds. That's where one molecule transfers over an electron to another molecule. For example, if I look at this molecule here, it has a single electron in its outermost electronic orbital. It's actually sort of a spare electron in a way. It wants to give it away. If there's a molecule nearby that is sort of missing an electron, it needs one more electron to form 8 electrons in its outermost molecular orbital to become stable. It will take that electron, and that is what is known as an ionic bond. So this molecule becomes positively charged. This molecule becomes negatively charged. They are both attracted toward each other then. Another way to form a bond is actually to share electrons. If I have 2 atoms, each which would like one more electron to make an octet, they can just share a pair of electrons, one from each. Notice now I have 8 electrons around this atom, and I have 8 electrons around this one. That is a shared electron bond, or what we know as a covalent bond. There are 2 other types of bonds. The first one is a metallic bond, where the metal atoms are located next to each other and the electrons are located in between the different atoms in crystal lattices that are formed by the metal atoms. We won't talk about these types of bonds this semester. The 4th type of bond is a special type of bond, and that's a bond between hydrogen and either oxygen, hydrogen and sulfur, or hydrogen and nitrogen. And there is some sharing of electrons that goes on. We call this a hydrogen bond, and it's a special bond, and we'll talk more about that as we move through some of the subsequent chapters. For now, we're going to talk mostly about ionic bonds and covalent bonds. It is the electrons in the outermost valence shell that is responsible for bonding in both ionic and covalent bonds. Let's take a look at those. So the electrons in the outermost shell, we call those the valence electrons. If I look over here in column 1A, and we look at the top here, hydrogen has 1 valence electron in its outermost shell. I go down 1 element in the periodic table. Lithium has 1 electron in its outermost valence shell. And I keep on going down. Same thing with sodium, potassium, and all the way down this column right here. If I move over 1 column over to 2A, those elements contain 2 electrons in their outermost shell, as shown here in beryllium, which has 2 electrons in its outermost shell. Those electrons are 2s2 electronic configuration. I'm going to skip all these intertransition metals, which are mostly form metallic bonds. Over here to group 3A, like boron, it contains 3 electrons in its outermost shell. Elements in column 4A contain 4 electrons in their outermost shell, like carbon. Elements in column 5A contain 5 electrons, and I keep on moving down. Oxygen, 6, the halogen, 7, and all the way over here to the noble elements, they contain 8 in their outermost shell. These electrons, these valence electrons, are the ones that are most responsible for bonding in both ionic bonds and covalent bonds. Now, noble gases are particularly stable because their outermost shell is full of electrons, which means low energy. So helium has 2 in its outermost shell, so its outermost shell is full. Neon has 8, argon has 8, krypton has 8, xenon has 8, radon has 8. We call that an octet. And those octets are stable because they have a full, complete outermost shell, which is low energy. All the other elements in the periodic table want to actually share electrons or exchange electrons to actually form that octet or that noble metal electronic configuration. So main group elements react so that they can obtain that noble metal electronic configuration. They want that full outermost electron shell, which in most cases, except for the helium and hydrogen, is going to be 8 electrons, or an octet. So let's look at some of the main group elements, elements that can lose an electron to achieve that octet. For example, sodium. If it loses 1 electron, its outermost shell now has 8 electrons in it, and so metals tend to lose 1 or more electrons to obtain that octet. In other words, they want to look like the electronic configuration of a noble gas. Like in this case, sodium attains that electronic configuration of neon. Main group elements can also gain electrons to achieve an octet in their valence shell. For example, chlorine, which is a halogen, and it is in group 7. It has 7 electrons in its outermost valence shell, so it would like to gain an electron. When it gains an electron, it has 8 electrons in its valence shell, and so it now has the electronic configuration of argon. So in general, nonmetals, those elements over on the right-hand side of the periodic table, tend to gain 1 or more electrons to attain the noble gas configuration. So where do these electrons that we either gain or lose come from, and where do they go? It turns out they go to another element. And so, for example, I have sodium that wants to lose an electron. If I put it near an atom of chlorine that wants to gain an electron, they will exchange that electron. So sodium loses it to attain an octet, and chlorine gains it to attain an octet. So now I have sodium that's positively charged and chlorine that's negatively charged. Those two charges attract each other. That is what is called an ionic bond. If I have 2 nonmetals, they tend to share electronics to achieve that octet of electrons in their valence shell. We're going to call this a covalent bond. So for example, if I have chlorine and I have more chlorine atoms, each of them wants to gain 1 more electron. They can do that by actually coming together and sharing that electron, and that is what is known as a covalent bond. And we're going to see in this chapter why that is energetically favorable, why 2 chlorine atoms would want to come together and form a covalent bond. Chemists count shared electrons as being part of both atoms. So that's why we can take these shared electrons and call these 8 around this chlorine and call it 8 around that chlorine. Let's take a look at chlorine actually forming a covalent bond with itself and compare it to chlorine forming an ionic bond with sodium. So in a chlorine-chlorine covalent bond, which we're going to call a molecular compound now, it is held together by discrete molecules actually sharing electrons. If I go over to sodium chloride, which is an ionic compound, sodium chlorine and chlorine are held together in a crystal lattice by electrostatic charges, meaning the cation sodium is attracted to the anion chlorine after they've exchanged electrons. If I look at the properties of Cl2, it is held together by a covalent bond. It is a yellow-green gas at room temperature. Its melting point is minus 100.98 degrees C. Its boiling point is minus 34.5 degrees C. So if I take chlorine gas and I start cooling it down, when I reach minus 34.5, it becomes a liquid. When I cool it down further and I reach minus 100.98 degrees C, it becomes a solid. If I look at sodium chloride, it's actually a white solid at room temperature. I need to heat it up to 801 degrees C to actually start melting sodium chloride, and I need to further heat it up to 1465 degrees C to actually boil sodium chloride. And you can see here in these pictures, at room temperature, chlorine gas, Cl2, is contained in a gas cylinder, whereas sodium chloride is a white crystalline salt. We can actually generalize a little bit about molecules that are formed by covalent bonds. They can either be solids, liquids, or gases. They typically have low melting points and low boiling points. If we were to generalize about compounds that are formed by ionic bonds, those are actually often crystalline solids with very high melting points and high boiling points.